Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Karnaugh Map Examples. At this time, you should be pretty well versed at mapping 3 and 4 variable expressions and then grouping those ones in there inside a workable, minimized SOP expression. Okay, that was one of our previous lectures dealing with that. And now what this lecture is just a bunch of examples of doing this. Since we left off on groups, mapping, real easy. 3 variables, just here's our 3 variable map, and I'm going to call this X, Y, Z, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. All those addresses are 1, 2, 3 zeros. And I could start thinking in terms of 2, 3, 4, 5, 6, 7 for binary numbers if I want to. These are just kind of little cheat sheets here for you. So W, X, Y, Z. We're always doing that in gray code. Otherwise, it's not going to work. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, binary number equivalents. That should be pretty easy. We kind of left off at groups, and that's the hardest part, actually. So let's review groups. What are the 3 steps? We want to group the ones. Step 2, determine that group product expression, ignoring all those subrules. And number 3, sum the groups. We're coming up with a minimum SOP expression. That's the whole purpose of putting these expressions into KMap, is to come up with a minimum logical expression. Rule number 1's got a bunch of subrules there, okay? So maximize the size of the group, minimize the number of groups. Those are guidelines right there. It's going to give you the minimum SOP expression. What are the sizes of groups? They're groups of 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. You get the picture. Powers 2. The cells must be adjacent. North, south, east, west. They're adjacent. Left edge, right edge. They're adjacent. Top and bottom. They're adjacent. Diagonals, not adjacent. Easy. Pick the largest group. Basically expand that thing out. If there's ones in the neighborhood, make sure you get a 1, 2, 4. Make the biggest one possible. Last one there, each one must be in a group. You can't just have a 1 hanging out there, because then you don't have the full expression. Finally, overlapping is possible. Okay, so basically I'm going to expand it out to make the biggest group possible, even though I might be encroaching on another group's territory. Okay, and this is what I want to show is a couple simple examples of just some K-maps, and let's just talk about groups. Just forget all this stuff about mapping and everything like that. Don't forget about it, but we're going to come back to it. So let's just talk about groups. So here I'm going to draw a group for you. Let's call this example 1. There it is. What type of K-map is it? Oh, it's a 3 variable expression. What's our domain? X, Y, and Z. Whether I derive this from a truth table or an SOP expression doesn't matter. Let's just do a grouping exercise. I'm going to grab a group of 2 right there, right? I'm going to grab a group of 2 right there. I'm going to grab a group of 2 right here. The question is, do I need that green group? Okay, common misconception. You don't need that green group, because again, remember, maximize the group. What's that rule? What's the rule immediately beyond that? Is minimize the number of groups. Why would I ever include that green group in there? Because all those ones are already accounted for. I know overlapping is possible. Why would I ever do that? Let's do this expression. So the terms in red, what is that? Well, it's X, Y, Z. The way we've organized our KMap, it's 000, 0, 1, 0. What matters? Well, X is always a 0, so I'm going to put X and then invert it, because it's always a 0. Why does it matter? Because it can be a 0 or a 1. Z is always a 0. There you go. So I'm going to put a Z with a bar over it. The term in blue is X, Y, Z, 0, 1, 1, 1, 1, 1. What are the terms that matter? Well, X doesn't matter, because it could be a 0 or a 1. Y always has to be a 1, so I'm just going to put Y. I'm not going to negate it. And Z always has to be a 1, so I'm going to put a Z and not negate it. So my final SOP expression, let's say, because we're running out of X's, Y's, and Z's, let's say W is equal to not X and not Z, or Y and Z. That is the minimum SOP expression. If I did this wrong, I could recognize within my answer, within my final answer. What I'm saying is, if I come up with my final answer, are there any Boolean laws that I could potentially use to simplify this? The answer is no. You might be tempted to think Z or not Z, but it's no, it's not, because that's an X term, that's a Y term. Actually, it's a not X term and a Y term, so this can't get those out of there. But if I did this thing incorrectly, I would notice opportunities to simplify. Well, let's try that. Let's include that green group in there. So green group, I'm accidentally putting that in there. X, Y, Z. What is it? Well, let's not use that listing out. It's always in the row where X is always a 0 and Y is always 1. Z can take a value of 0 or 1, so it doesn't matter. It looks like what I need is not X and Y. So what I'm getting is an incorrect answer. W is equal to not X and Y, or, and I'll try to do the colors here, not X and Y, or not X and Z, or Y and Z. You look at here, not only is it a longer expression, it's not the minimized expression because I recognize opportunities. I could potentially factor out that not X term there. I could potentially factor out the Y term right there and do some Boolean simplification. And you know what it's going to happen when you do your Boolean simplification? You're going to get that as your result. Why do the extra step there? Why include that extraneous term? It's a good example is, I say maximize the size of groups. Step B, minimize the number of groups. Don't put stuff in there that you don't need. Okay, let's go ahead and do another example just dealing with grouping. Let's call this example 2. Okay, here's example 2. I've got a 3-variable Karnaugh map. What are my variables? Square, triangle, star. Doesn't matter the name of those things. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. What are the groups that I'm not going to use square, triangle, star. That'll be silly. CBA. There you go. What are the groups you can think of? What are the groups can you find? That's a group of 2. That's a group of 2. This is a group of 2. And this is a group of 2. Or is the better grouping group of 4 via wraparound adjacency? The answer is it's better with a group of 4 via wraparound adjacency. Okay. What is the term in red? What is the term in blue? What is the term in green? Go ahead and figure it out. Okay. So what I'm going to do is I'm going to try to do a little shortcut here. I know I could list these things off, but look at the term in red. C is always a 0. Look at those C's. A is always a 0. Looks like B doesn't matter. So what I'm going to say is not C, not A. Do the analysis. CBA for all those terms. 0, 0, 0, 0. Excuse me, 3 zeros. 0, 1. 0. What are the terms that matter? Looks like A always has to be a 0, so not A. C always has to be a 0, so not C. B doesn't matter. What do I get? The same thing as I did with my shortcut. Doesn't matter which method you use. The little shortcut, obviously faster. Okay, what's the term in B? No, excuse me, the term in blue. Looks like that is CA. So we've got not A, not C, and C and A, or excuse me, or C and A. So if I left it alone, that might be one of those gates that we've been dealing with there, essentially an exclusive NOR between A and C. But we've got this green term in there. Just if you understood what I'm talking about there, don't worry about it if you didn't. Green. Okay, so what is green? CBA. Let's go in green though. CBA. You can go ahead and list all those terms, but I'm going to look at the shortcut. I see in that row B is a 0, and I see in that row B is a 0, so it's definitely B, not B. And then I see it takes up both columns in A, so A doesn't matter. So what I'm saying is that term in green is not B. Don't believe me? Do the whole analysis. CBA, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1. Looks like C doesn't matter. Looks like A doesn't matter. B always has to be a 0, so not B. All right, my final expression, let's call it X is equal to not C and A, not A, or C and A, or not B. What can I see and what can I kind of elucidate about the behavior of some of these 3-variable Karnaugh maps? If there's one term in a group, it's going to have all the variables, A, B, and C. So I'm going to give you some general rules. 3-variable Karnaugh maps. If there's one, how many terms will it have? So let's see, size group, terms. If there's 1 in it, it's going to have all 3 terms. If there's a size 2 group, it's going to have 2 terms. If there's a size 4 group, i.e. that green group, it's going to have 1 term in it. If it's a size 8 group, i.e. look at this, world's easiest K-map. What's my expression? Boom, my expression is 1. Tie the whole thing to logical high. My expression 8, there's no terms in it. Okay, it's logical 1. It's all ones. So that's kind of a rule of thumb with 3-variable K-maps. If you ever get a size of a group with 4 in it, and you're somehow coming up with 3 terms, you're doing it wrong. Okay, those are good rules of thumb. Okay, let's do a couple grouping examples for 4-variable Karnaugh maps. So here's a 4-variable Karnaugh map, and look at my variables. D3, D sub 3, D sub 2, D sub 1, I should write, and D sub 0. It's all one number. If you could imagine a 4-bit binary number, let's say for example, it's a BCD number, 1, 0, 1, where this is the MSB. That's the LSB. It's going this way. What is it representing? It's representing decimal number 9. You will see this notation very shortly when we start dealing with a lot of adders there. Those are the variables. D3, D2, D1, D0. It's almost kind of like that standard logic vector format that I used in VHDL. Just assigning MSB to LSB. And standard practice is you put your MSB on the left. That's the highest. Okay, so for an 8-bit, it'd be D7 all the way down to D0. What's my MSB? That guy. Okay, but I digress. Here's the K-map. Tricky. And just to be a little more tricky, let's throw that guy in there. Let's throw that guy in there. Find the groups in this 4-variable K-map. I'm going to go for the easiest one first. That's a group of 2. What is it? Well, it's always in the column D3, 1, D2, 0. So what I'm going to say is D3, not D2. What's the row? Excuse me. It was in the D3, D2, 1, 0 row. What are the columns that it's in? Well, it's in a column where D1 is a 1, D0 is a 1, D1 is a 1, D0 is a 0. It looks like D0 doesn't matter and D1 does. So that's the expression in red. If you want to go ahead and do the old-fashioned way, D3, D2, D1, D0, what are the variables that matter? Excuse me, what are the binary equivalents for those addresses? It's 1, 0, 1, 1, 1, 0, 1, 0. And like I said, there's your D3, not D2 term, because they definitely matter. D3 always has to be a 1. D2 always has to be a 0. What is D1? Well, D1 matters, and it always has to be a 1. D0 does not matter, so get rid of it. We came up with the same expression with our shortcut. Now, let's grab another group. How about this group of 4 right here? And by the way, that's that expression right there. What's that group of 4? Well, I'm going to say D2 and not D1. Am I correct? Try the full-on listing of these things. Try the shortcut. Either way, you're going to get D2 is 1. Notice D2 is always 1. In these columns here, D1 is always a 0. So my expression for that blue group should be D2 ANDed with not D1. All right, I'm going to get rid of these arrows because I want to draw something here. What are the other group or groups that you see here? One might think this big old group of 4 here. That's awesome. Again, maximizing the size of the groups. You might think that you're doing awesome. And you might think you're doing doubly awesome because you've got 2 groups of 4 and everyone's going to be so proud of you. Well, check it out. I'm going to turn you back because look, via wraparound adjacency, the left is adjacent to the right. I can make a giant group of 8. Okay, so I'm maximizing my groups. What's the terms in green? Okay, so it's D3, D2, D1, D0. It's taking the combination of 0, 0, 0, 0, 0, 1, 0, 0. Do you see how exhausting that whole listing thing becomes? Just start thinking in terms of shortcuts here. Obviously, D3 and D2 have nothing to do with it because D3 is taking the value 0 or 1. Look at D2. It's taking the values of 0 or 1. It has nothing to do with it. The columns. D1 is a 0. D0 is a 0. I'm going to remove this over here. This column. D1 is a 1. D0 is a 0. What's the common term? Looks like D0 is always has to be a 0. So the expression is not D0. Don't believe me? Go ahead and do all 8 possible combinations. You'll find that D0 must always be a 0 for that particular group. What I've come up with here is my final expression, and all I've got to do is just put them together. So what is step 3 is basically sum those product terms. D3 and not D2 and D1, or not D0, or D2 and not D1. I know it's confusing using those little numeral notations, but this is going to be incredibly handy when we deal with numbers coming in where there's a position away, i.e. numerical values, where you have to keep track of those things. Like I said with the 3 variables, there's kind of rules for 4 variable expressions too. So the size of the group, the number of terms. If I've got 1, there's only one in my group. I've got to have all 4 terms. If there's a size 2, think about the red expression, I'm going to have 3 terms. It's got D3, D2, and D1, some permutation of them. If I've got a size 3 group, you're doing it wrong, man, because there's no such thing as a size 3 group. There's a size 4 group. Look at the blue. Look at the blue group there. How many terms does it have? Well, obviously it's following our order. It's 2 terms, namely D2 and not D1. Finally, size 8 group. What are you going to get? You're going to get one term that matters. And if you're filling up the whole truth table with 16, you're going to have 0 terms that matter, i.e. everything is a 1. Some people ask me, okay, you've done 2 variables, 3 variables, 4 variables. Can you do 5 variables? Yes, you can do 5 variables. Can you do 6 variables? Yeah, you can do 6 variables. Can you do 7 variables? Yeah, not the easiest. Can you do 8 variables? Yes, I can kind of understand that. 9 variables? No. I'm going to use a computer. And I'm not going to make you do this in class. We're going to limit it to 4. You know how we went from 3 to 4? We just kind of added dimensions. If you go to 5, you could imagine, check this out, a K-map, a 4-variable K-map on top of a 4-variable K-map, where now I can have groups up and down too, where this represents the 5th variable 0, and that's the 5th variable 1. Pretty cool, huh? Now try 6 variables. Check this out. 4 K-maps on top of each other. I know some of you guys' head just exploded. Where that's 0, 0 of the 5th and 6th. That's 0, 1 of the 5th and 6th. 1, 1 of the 5th and 6th. 1, 0 of the 5th and 6th. And again, you can go into those things. And I used to know how to do 7 and 8s by myself, but man, for the life of me, someone asked me the other day, and in my head just kind of went blank. The point of the story is there are software utilities. I'm going to make a link to on our Moodle webpage how to do some of these things. And if I think 5 and 6 beyond 4s, I think they charge you for. The other thing with those Moodle links that I'm giving you for these K-map generators, they are awesome practice problems. You populate a K-map or populate a truth table, and you developed the minimize SOP expression, and hopefully you're coming up with the same minimize SOP expression that they came up with, and it's just giving you this instant feedback. Hey, am I doing this right or wrong? Because guess what I'm going to do on an exam? I'm just going to give you a K-map or a truth table or an expression. I'm going to say, come up with a minimum SOP expression, and you should come up with the same thing I do. All right, let's do one more example of just grouping for a 4-variable Karnaugh map. This one's a little bit tricky too. Okay, so here's another 4-variable Karnaugh map here, and just go ahead and draw your estimate of what the groups might look like. And I'm gonna do some wrong answers first. Okay, why is that a wrong answer? Make the group as big as possible. Again, via adjacency, norths and souths are all adjacent to each other. Here's another wrong answer. Why is that one wrong? Well, you just told me norths and souths are all adjacent to each other, but the deal is you have to do groups of 1, 2, 4, or 8. Okay, so there's no such thing as a group of 3. Here's another incorrect example. No, it don't work because you're not going to get the minimum SOP expression. Why not extend that thing all the way out over to here? Well, that's wrong too, because check it out. You got a group of 8 right below you, because again, north and south are adjacent just as east and west are. Why not just grab that whole group of 8 right there? Okay, see if you come up with a product term for red, blue, and green, and stick them all into one fully minimized SOP expression. And what I'm going to come up with for the red is not B and A. And you might say, how the heck did he do it that fast? Well, check it out. They're all in the column not B, or B0, A1. So it's obviously not B and A. What's the terms in blue? Put a sum. Blue is definitely C. Okay, because look at this. C right there. D doesn't matter because it's a 0 or 1. And it's in column 1, 0 for BA. So B is a 1, A is a 0. And finally, what is my terms in green? What's my product term for the group in green? Well, D has to be a 1. If you could look at the row right here, D has to be a 1. C is obviously taking 1 or 0. Doesn't matter. B is obviously taking 0 or 1. Doesn't matter. So that's D. Okay, so my final expression, X, whatever it's called, is equal to not B and A, or C and B and not A, or D. All right, and you could just as easily have done the listing out of all the binary combinations that make that possible and figure out what those terms are, but it's pretty easy to start using these shortcuts. Okay, let's do a couple more examples of these things, and those were just grouping. Example 1, 2, 3, and 4 were just grouping. Sometimes that's the hardest part. I didn't want to confuse you with those things. Now I'm going to kind of throw a couple more tougher examples at you where I've got an SOP expression. Maybe it's the full SOP expression, maybe it's not. Maybe you have to expand. I might give you a truth table, and you should come up with a minimum SOP expression, and you just never know what's around the corner. So here's example 5. Okay, let's say you walk around the corner straight into this ugly looking guy right here. It's X equals an SOP expression. Is it a full SOP expression? To me, it looks like it because I've got product terms which include terms of the whole domain, A, B, and C. Okay, so I don't have to expand it. I don't have to do anything funny with it. I'm going to go ahead and try to put this into a Karnaugh map. So what are the binary combinations for this first product term here? Well, A0, B1, C1. Second one, 1, 0, 1, 1, 0, 0. So those are the three terms I need to put into my Karnaugh map, draw on my Karnaugh map. I'm giving them in the order A, B, C. And let's just do something crazy. You want to do something crazy? Let's do something crazy. A, B, C. Fill out a Karnaugh map on its side. Fill out a Karnaugh map this way. 0, 0, 0, 1, 1, 1, 1, 0. 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. You're gonna get the same answer. I guarantee it. 0, 1, 1. There. 1, 0, 1. There. 1, 0, 0. There. Fill it out for the one on its side. 0, 1, 1. Right there. 1, 0, 1. Where is it? There. 1, 0, 0. Right there. Group the one on the left. Group the one on the right. I'm going to grab that group of 2 and that group of 1. I'm going to grab that group of 2, that group of 1. In red, the product term is A, not B. The group in blue, it's not A and B and C. One on the side, what is that? That looks like it's definitely A. And it looks like B is always a 0, so not B. Oh my gosh, what's this one? Looks like A is a 0, B must be a 1, C must be a 1. Come up with a final SOP expression for X, final minimized SOP expression, A and not B, or not A, B, C. Truth table, Karnaugh map on the side. What do we get? The same answer. It doesn't matter how you orient these things. I've actually never done that before, but very exciting. Which one do I like? I like this one. I don't know, just because I've always used them that way. Let's try another example. So here's example 6. Looks like it's another 3 variable problem, but there's an issue here. Do we have the full SOP expression? And the answer is no, because look at this guy right here. We got ABC, we got ABC, we got AC. We don't have the full SOP expression, so I can't really get all possible combinations. We can go ahead and expand that out to the full SOP expression. And there's a number of ways to do this. ABC or not A, B, C, or what's our missing term? It's B, so multiply it by 1. What's 1? Well, according to our Boolean rules, B or not B. A, B, C, not A, B, C, or not A, B, not C, or not A, not B, not C. There's a way of doing that, bringing it out to its full SOP expression. I could just as easily realize that this is called numerical expansion, a little side trick to do this. Well, if A, C, 0, 0, what's my B, C? So if that's got to be 0, what possible combinations am I missing? Well, I'm missing A0, B0, C0, A0, B1, C0. So what are those? It's those 2 possible combinations where I've already got 1, 1, 1, 0, 1, 1. That's called numerical expansion. That's another tricky method of doing it. One way you could also do this is do the full-on truth table, write out A, B, C, all possible combinations, and find when not A and not C. Well, right there and right there. Those would both have 1. And you can just easily fill out A, B, C, 1, not A, B, C, 1. So there are 3 ways of doing it. SOP, full expansion, numerical expansion, and the old-fashioned truth table method. What are you going to get? Regardless, you're going to get a truth table if you've ordered it in the following fashion. A, B, C, 1, 1, 1, 1. What is the groups? What are the groups that I can possibly get? And this might look similar to you. That group right there, that group right there. What are the terms in that product term? Well, look at on the left-hand side. It's always in a row that has A being a 0. It's always in a column where C is a 0, not A and not C. What's the blue one look like? Well, it's always in a column where C is a 1. It's always in a row where B is a 1. So our final expression for that X is equal to not A, not C, ORed with BC. Does this look familiar? Does the work of this thing look familiar? Well, it's example 1 up here. We came up with the expression not X and not Z, this one, ORed with Y and Z, that one, because it was called X, Y, Z. Example 6, we came up with not A and not C, ORed with B and C, because it was called ABC. Okay, so there's a finite number, the finite combination of these things that you can possibly get. It's just the names of those variables. It doesn't really matter what the names are. You should come up with kind of the same format. The only difference between example 1 and example 6 is I gave you a partially completed SOP expression. You can either fully expand it, do numerical expansion, or stick it in a truth table. Ultimately, you're going to be able to put those things into a K-map and get an expression. Okay, so let's move on from 3 variables. Let's go on to a 4 variable K-map example. Okay, so here's example 7. Is it a fully expanded SOP expression? Yes, it is, because all product terms include all variables of that domain, namely A, B, C, and D. But I'm throwing a little trick in here. Notice the order of these guys, A, B, C, D, versus the order of these guys, D, C, B, A. And I'm purposely messing with you. Figure it out. How are you going to organize these things? They're both equal. A to D, D to A. I don't care. Either way, you're going to come up with the same answer. What are the product term binary values that will give these things a 1? Well, this one's 0, 1, 1, 0. That one's a 1, 1, 0, 1. In the order A, B, C, D. A, B, C, D. Which order you want to go? You want to go A, B, C, D, D, C, B, A. It doesn't matter. This one is 1, 1, 0, 0. If I want to, let's go ahead and put these over here in one spot. A, B, C, D. So for the first one was 0, 1, 1, 0, 1, 1, 0, 1. The second one was 1, 1, 0, 0. The third one was 1, 1, 1, 1, 1, 1, 1, 1. Just because I want to make life confusing, do it in DCBA orientation and ABCD orientation. So 0, 0, 1, 1. 1, 1, 1, 1. What's the first one in DCBA orientation? 0, 1, 1, 0, 1, 0, 1, 1. They're the same. Put them both in separate K-maps. How am I going to organize this K-map? DCBA? No. A, B, C, D. How am I going to organize this K-map? D, C, B, A. Why am I doing that? It's easier to orient. It's easier to find where I'm at. 0, 0, 0, 0. Because now I know 0, 1, 1, 1, 1, 0. I know 0, 1. I'm in this row. 1, 0. I'm in that column. I'm right there. Put a 1. If I had to go the other way using that K-map, i.e. from here to that K-map, it's a little bit harder. You can do it. Put a hat on your foot. Okay? And I'm going to prettify these things. Okay, so go ahead and fill out the K-map on the left. And if you want to, fill out the K-map on the right. And let's just do the one on the left together. So 1, 1, 0, 1 right there. 1, 1, 0, 0 right there. Quadruple 1 right there. So now fill out the truth table on the right by yourself, and you should look something like this. There you go. Let's just do the one on the left right now. Find the groups. This one's pretty challenging, okay, because where are the groups? I got a group of 3. Wrong. How about a group of 2? How about another group of 2? They're adjacent. They're overlapping. How about a group of 2? Wrong. It's diagonals. They're not adjacent. Okay, how about a group of 1? What are the product terms for the one in the red, product terms for the one in the blue, and the one in the green? Ultimately, we're going to sum them all together for our final expression. What was it? I never gave you a value. Let's call it Z. What is the red? It looks like it's A and B. They're in that row. They're always ones, A's and B's. What's C and D? Well, it looks like C's always a 0 for the term in red. There you go. What about blue? Let's use a different method of analysis. A, B, C. List out everything in there. It is 1, 1, 0, 1. D, by the way. I forgot that one. What is the next one? It's 1, 1, 1, 1. What are the terms that matter? A's got to be a 1, B's got to be a 1, and D's got to be a 1. A, B, D. Again, we're following kind of what we've talked about for general rules of thumb. For 4 variable K-maps, a size 2 group will have 3 terms. Makes sense. If I did it wrong, I'd have 4 terms in one and 2 terms in another or something like that. It's the wrong answer, basically. All right, what am I getting for the group in green? Well, it's a group of 1, so I've got to have all 4 terms. A, B, C, D. What is A? A is a 0. B is a 1. Leave it alone. C is a 1. Leave it alone. D is a 0. Try this for the other K-map, and I guarantee you'll get the same answer. Yes, it'll look different in the K-map. You're going to get the same final, fully minimized SOP expression. There's a group of 2. There's a group of 1, maybe coincident with the other group of 1 that we have. Where's the other group of 2? I see a group of 1 there. That's incorrect because we can maximize the size of the groups by wraparound adjacency. Okay, what's in red for this one? ORed with what's with blue, ORed in green, or red. It's always in a column where B and A are 1. It's in a row where D is a 1. C doesn't matter. Blue. What's the thing in blue? It's always in a row where always in a column where B and A are 1. What is the third variable? looks like. C can always be a 0. D doesn't matter. Okay, finally, our green term, it's a group of 1 in a 4-variable K-map. I've got to include all terms A, B, C, D. Its combination, though, is 0, 1. Notice how I'm tricking you up here, because what is this thing oriented? It's D, C, B, A. That combination is 0, 1, 1, 0. Notice I've written it A, B, C, D. So it's 0D, C1, B1, A0. I can make my life so much easier if I just went D, C, B, A and read it. 0, 1, 1, 0. Have we come up with the same expressions? A and B and not C. A and B and not C. Or A and B and D. Or A and B and D. Or not A and B and C and not D. Or not A and B and C and not D. It doesn't matter the implementation in which you, or the order in which you implement this thing, you're gonna get the minimized SOP expression if you do it correctly. Okay, let's bring this to a close with our K-map examples with example number 8. And here is an expression. It's a partial SOP implementation. Is it the minimum SOP implementation? I don't know. We might be able to use our Boolean laws to figure this thing out. We might just be able to use a K-map. And there are, again, easy ways and hard ways to do these things. One might be tempted to go ahead and expand this thing out to a full SOP expression for this domain. What is the domain of this? Well, there's A terms, B terms, C terms, and D terms. Just think of this example A. I've got to expand it out into B or not B. I'm just dealing with that one. All the other ones are staying the same. So I get A, B, or A, not B. Then I've got to expand both of those guys out to A, B, C, or not C, or A, not B, C, or not C. And then once I get A, B, C, or A, B, not C, I've got to expand and all these, D or not D. I've got to expand it out to D or not D, and da-da-da-da. That's going to take a lot of work. I'm not going to do that. I'm leaving that as an exercise to you, because I'm just going to do a shortcut. I'm just going to do the truth table, which is kind of like numerical expansion, which I referred to earlier. Is numerical expansion, if you remember right, I referred to it. Just take this term, A, B, C, D. A is always 1. B, C, and D can take all possible combinations, 000 to 111, where A stays 1, all the way through. Just look for those spots in the truth table. Okay, so let's go ahead and make a 4-variable truth table and do it for this term, do it for that term, do it for this term, do it for that term. You got your full truth table. Let's take that whole truth table into a K-map and bang, it's done. Okay, so let's go ahead and have a blank truth table. Okay, so there's my bare truth table. How am I going to organize it? A, B, C, D. I could do DCBA. Why would I do that? Because I've already got one term written that way. And let's just do easiest to hardest. Well, depends on your perspective. Let's do this product term. Not A and B and C and not D. What is that? That's 0, 1, 1, 0. Find on the truth table where 0, 1, 1, 0 is. Right there. Put a 1. Okay. What's this guy? Well, it's A, 1, C, 1, D, 0. Okay. Notice I'm missing the D term, excuse me, the B term. Oops, I'm going to write it right. 1, 1, 0. B could take the value of 0 or 1. Find those two spots on the truth table. 1, 0, 1, 0, right there. Put a 1. 111, put a 1. Another way, and this is what I call the truth table method, is don't worry about B because it doesn't matter. Just look for combinations of A1, C1, D0. Where are they? Right there and right there. Okay, you might be able to just jump to that. Let's try that method here. Let's try that with this one. Okay, let's kind of use the truth table method. Where is C a 0 and D a 1? Look in the truth table. I'm going to call that pink. So C a 0, D a 1. Right there, right there, right there, right there. Does it matter what A and B? Well, A and B could take the forms of 0, 0, 0, 1, 1, 0, 1, 1. What do I have? I've got 0, 0. 0, 1, 1, 0, 1, 1. Okay, so the truth table method is just kind of a truth table shortcut, is kind of just numerical expansion without really writing it out. Again, what am I going to do with those? Put a 1, put a 1, put a 1, put a 1. Finally, this last one, this one is easy. A or. Just find where A is 1. Right there, there, right there, right there. And this one, and this one, and this one, and this one. But it's already accounted for. What do you want me to do? Put a 2 there? Well, I can't. because it's binary. So the numerical expansion, the full-blown SOP expansion, or kind of this truth table shortcut is going to give you that correct implementation of the correct starting place for the Karnaugh minimization. What do I do with the rest of it? Put in zeros. Get rid of these funky colors, and now K-map it. What's my 4-variable Karnaugh map look like? A, B, C, D. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And this is how I like that little cheat sheet. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, whoops, 10, 11, 12, 13, 14, 15. Because if I remember my binary combination, it counts from 0 to 15. So that's 1, 2, just write them next to it. So it looks like I've got a 1. Where is the 1? Right there. So I'm talking about is that one right there. Where is it in my grid? I've got a 1 in position 5 right there. I've got a 1 in position 6. Where's position 6? Right there. I've got a 1 in position 8. Where's position 8? Right there. I've got a 1 in position 9 right there. 1 in position 10 right there. 1 in position 11 right there. 1 in position 12, 13, 14, 15. 12, 13, 14, 15. There's my minimized K-map. There is my K-map from which I can derive my minimum SOP expression. Okay, start grouping it. Big old group of 8, group of 4, group of 2. What is the expression for the one in red? Or it with the expression for the one in the blue? Or it with the expression for the one in green? Does this look familiar? It should look familiar because it was example. Which example? Example 4. You're going to get a different answer. Why are you getting a different answer? Because the names of the variables are different. The D is considered the MSB in this one, whereas the A is considered the MSB. Notice the orientation A, B, C, D. You're going to get A is the MSB. What is red? The red product term. It's in this row where A is always a 1. What is this blue product term? Well, it's a group of 4, so it should probably have 2 variables in it. For a 4 variable, it's not C and D. Finally, what is green? It looks like it's B, C, not D. Check your work. Okay, we're looking at, and that is our final minimized as expression for this without even using any of those Boolean laws. What did we do? We didn't even use the SOP expansion, but we could have if we wanted to. We used that truth table shortcut, which is kind of a subset of the numerical expansion, and we just put it in a K-map, spit out the K-map with the results. We have discussed all about the behavior of bears and bear traps and how to spring a trap on a bear, i.e. what we've discussed is the SOP expression, the K-map, and then how to use the K-map. We have not yet discussed how to lure that bear into the trap in the first place. And what I'm talking about is we have never discussed developing an expression, i.e. developing a truth table. And this is the art form, which is really kind of it takes some practice. I'm going to give you some systemized methods to it. And what we're going to do is we're going to kind of learn the art form of luring that bear in a trap. How do we get a truth table? And once we've got a truth table, you know all the rest. You already know how to do a K-map. You already know how to minimize the SOP expression and get that minimum logical expression. So what we're going to do is talk about next is examples of how to develop truth tables. Some of the tips and techniques that we can use to develop truth tables, and then from there, use a K-map. You derive that minimum SOP expression. You don't have to worry about any of those Boolean rules, okay? So that's on to our next lecture.